Good morning, dear students. Let us start our next semester, your fourth semester, with spectroscopy. Have you heard of the spectroscopy? Normally, the spectroscopy it is used for determining the structure of molecules and used for determining the structure of atoms and molecules. Used for determining the structure of atoms and molecules. So using this spectroscopy itself, we are determining or identifying the structure of a particular atom or a molecule. That is, for example, ammonia. It has got a pyramidal structure. Then water molecule, it has a V-shaped structure. So these structures are determined with the help of spectroscopy. And also this spectroscopy, it arises, or this branch it deals with the study of the interaction of electromagnetic radiations. Have you heard of this electromagnetic radiations? Electromagnetic radiations means they are a group of radiations, that is, for example, cosmic rays, radio waves, then microwaves, infrared, etc. Isn't it? Visible radiation, etc. These are all electromagnetic radiations. And when these electromagnetic radiations interact with any matter, or when these electromagnetic radiations interact with matter, means it can be in the solid form or in the liquid form. Okay. And when these electromagnetic radiations interact with this matter, what happens? A spectrum will be produced. So the spectrum will be produced, and this spectrum, it can be dark lines or it can be bands. Okay, the spectrum will be very bright lines, in the form of very bright lines, or it can be in the form of bands. Okay, so this type of interaction of electromagnetic radiations with matter, it is called as the study, it is called as spectroscopy. Okay, so with the help of this spectroscopy, normally we are determining the structure of so many complex compounds. For example, in phytochemistry, that is from plant extracts, so many chemical compounds are there in these plant extracts, isn't it? So we can identify the functional groups present in that particular plant extract or leaf extract, whatever it may be. Okay, so we can identify the functional group, we can identify the hydrocarbon chain present in that compound, we can identify the elements present in that particular compound, etc. So with the help of the spectroscopy, we are identifying all these things which are present in a organic compound or in an inorganic compound, whatever it may be. Okay. So simply saying, the spectroscopy is used to identify the structure of atoms as well as molecules. And second one, spectroscopy, it is the study of interaction of electromagnetic radiations with matter. Okay. See, normally what happens is that there are different energy levels for an atom or for a molecule. So these are some of the different energy levels. Let it be E1, then E2, E3, E4. So when this, suppose the atom, it is in the ground state, and when it will be having getting some energy, what happens? It will be excited to the next higher energy level. That means this atom will be absorbing some energy and will be excited to the higher energy level. And again, what happens is that after exciting to the higher energy level, that is to E2, sometimes it will be returning back to the ground state, that is the transition from E2 to E1. Okay, so while it is back to the ground state, what happens is that some energy will be released, isn't it? Some energy will be released or some energy will be emitted. Okay, so here if the atom, it is absorbing some energy, it will be excited to the higher energy state, and if it is emitting, or when it reaches back to the ground state, it will some radiations will be emitted. So what happens is that the energy difference between these two states will be equal to E2 minus E1, and also the energy released or emitted, or the energy absorbed, it is quantized, isn't it? The energy released or absorbed, it is quantized, and we can say that this E2 minus E1, the difference of the energies between the two energy levels, it will be equal to h nu. Okay. Therefore, we can say that nu is equal to E2 minus E1 divided by H. Okay. So, in this way, we can calculate the frequency of that particular radiation emitted or absorbed. Okay. So, then the next is the line spectrum or the atomic emission spectrum. Line spectrum or atomic emission spectrum. Line spectrum or atomic emission spectrum. See here, this line spectrum means see, normally if we are taking a spectrum, sometimes the spectrum will be having bright lines. You all know the spectrometer, isn't it? So this this spectrum, it will be having bright lines, and these bright lines, they are produced by the interaction of the electromagnetic radiation with atoms. So if the electromagnetic radiation are interacting with the atoms of a particular substance, a very bright lines are produced, and this type of spectrum, we can call it as the line spectrum or atomic emission spectrum. So it is atomic emission spectrum because it is produced by the interaction of electromagnetic radiation with atoms. Okay, or we can say it is line spectrum because very bright lines are produced, and the bright lines are somewhat closely spaced. Okay, so this is called as a line spectrum or atomic emission spectrum. It is very important. So the bright lines produced as a result of the interaction of electromagnetic radiations with atoms, it is called as the line spectrum or atomic emission spectrum. Hope you are clear. Then the next one, we can see the molecular spectrum. Again, molecular spectrum. Molecular spectrum means, again, what happens here, it is the interaction of electromagnetic radiations with molecules. Okay, it arises due to the interaction of electromagnetic radiations with molecules. And also here, this in molecular spectra, there are different types are there, or they have different energy levels. This molecular spectra has got different energy levels, and these energy levels are normally they are the rotational energy level, then vibrational energy level, and the electronic energy levels. Okay, so these are some of the energy levels in molecular spectra, and as a result of the rotational energy level, or if the transition it is between the rotational energy levels of a particular molecule, there arises the rotational spectra. Okay, so if the transition it is between the different rotational energy levels, there arises the rotational spectra, and if the transitions it is in between the vibrational energy levels, it is called as the vibrational spectra. And if it is between the electronic energy levels, what happens? It is the electronic spectra. Electronic spectra. Okay. So these are the different energy levels of molecular spectra. Molecular spectra arises due to the interaction of electromagnetic radiations with molecules, and also different energy levels are there in molecular spectra: rotational, vibrational, and electronic energy levels. And again, they arise as a result of the transitions in those particular energy levels. Different spectra will be arising. Okay. Next is the absorption spectra. So we have seen this line spectra or atomic emission spectrum. Then another category, that is the absorption spectra. So absorption spectra means it is the absorption spectra. Absorption spectra means this absorption spectra, it is they are dark lines. Okay, already we have seen the line spectra, it will be having very bright lines, but in the case of this absorption spectra, it will be having dark lines, and this dark lines, it is due to the absorption of radiation. Okay, this dark lines, it is due to the absorption of radiation. So that is the absorption spectra. That means when this electromagnetic radiation it is passed through a solution or a solid form, what happens? Some of the energy will be absorbed by the molecule and it will be excited, and some of the energy will be absorbed and some of the electromagnetic radiations will remain as such, or it will not be used up. So the radiations which are absorbed, that give rise to this dark spectra or dark bands. Okay, so this dark bands produced as a result of the absorption of radiation, it is called as the absorption spectra. Next we can go through some of the characteristics of electromagnetic radiation. There is no sense in teaching this characteristics of electromagnetic radiation for you mainly for the physics students. You have already studied all these things, and I think sometimes you might have done your practicals also in the spectrometer, isn't it? I hope it is like this. So some of the, anyway, I will be saying the characteristics of electromagnetic radiations also, and also this, according to Clerk Maxwell, this he proposed that the light will be propagating in the form of waves, isn't it? And these waves, it will be having, light will be propagating in the form of waves, and these waves will be associated with, and the waves will be associated with electric and magnetic fields. Okay, these waves will be associated with both electric and magnetic fields, and hence it is called as electromagnetic radiation. So we can define electromagnetic radiations are as the radiations which are associated with electric and magnetic fields. Okay, then going through the characteristics. First one, that is the amplitude of an electromagnetic radiation. Amplitude of an electromagnetic radiation. See, suppose this is an electromagnetic radiation, or this is a wave. See, this amplitude means it is the height of a crust. Height of a crust or depth of a trough. Height of a crust or depth of a trough. See, this is the crust, isn't it? This is a crust. This is also another crust. Then this is a trough. So this amplitude means it is the height of the crust. So this is the height of the crust, or this is the depth of the trough. So amplitude defines the height of the crust or depth of the trough of an electromagnetic radiation. And also this amplitude determines the intensity or brightness of the radiation. Amplitude determines the intensity or brightness of the radiation. So that is amplitude. Then the next one, that is the wavelength. Wavelength. Here wavelength means it is the distance between two adjacent crafts. That is this distance. This distance gives the wavelength. These are the two adjacent crusts, and these are two adjacent troughs, isn't it? These are the two adjacent troughs, and these are the two adjacent crusts. So the distance between two adjacent crust or trough, it is called as the wavelength. So this distance, it is called as the wavelength. Distance between two adjacent crust or trough, that is called as the wavelength. Usually wavelength, it is expressed in centimeter, meter, then nanometer, angstrom, etc. Angstrom, it is 10 raised to minus 10 meter. 1 angstrom is equal to 10 raised to minus 10 meter. 1 nanometer is equal to 10 raised to minus 9 meter. Okay. Then the next one, that is the frequency. Frequency, it is denoted by nu. Wavelength, it is denoted by lambda. Okay. Amplitude, it is denoted by A, small letter A. Amplitude A, wavelength lambda, and frequency nu. See, frequency means it is the number of waves passing through a particular point in 1 second. Number of waves passing through a particular point in 1 second, that is called as the frequency. See, suppose we are considering this point. So the number of waves passing through this particular point in 1 second gives the frequency of that particular radiation. So frequency, it is usually expressed in hertz. 1 hertz is equal to 1 cycles per second. 1 cycles per second. Then the next is the velocity. Velocity. So velocity, it is the distance traveled by a wave in 1 second, and velocity, it is denoted by the letter C. Velocity, it is the distance traveled by a wave in 1 second. That gives the velocity. And usually the velocity of all the electromagnetic radiations, it will be equal to the velocity of light, that is 10 raised to 8 meter per second. So all the electromagnetic radiations will have the same velocity, but they differ. They differ in their amplitude or such things, so or wavelength. Okay. So velocity, it is the distance traveled by a wave in 1 second. Then the next is the wave number. Wave number, it is denoted by nu bar. And also wave number, it is the reciprocal of wavelength. Reciprocal of wavelength, or nu bar is equal to 1 by lambda. Okay. Nu bar is equal to 1 by lambda. Wave number, nu bar, it is the reciprocal of wavelength. Nu bar is equal to 1 by lambda. Then the next one, that is the relation between lambda, c and nu frequency. Okay, that is what is the relation connecting these three: wavelength, velocity and frequency. C is equal to nu lambda. The relation is C is equal to nu lambda. Okay, velocity is equal to wavelength into frequency. That is the relation between these three. These all you know. Okay, so next is the electromagnetic spectra. Electromagnetic spectra. What is an electromagnetic spectrum? It is the arrangement of electromagnetic radiations in the increasing order of wavelength, or in terms of frequency. Okay, the arrangement of electromagnetic radiations in terms of wavelength or in terms of frequency, that is called as the electromagnetic spectrum. So here I will be writing the electromagnetic radiations in the increasing order of wavelength. Okay, so the first radiation, that is cosmic rays. Here lambda is increasing in this manner. Okay, cosmic rays, then gamma rays, then X-rays, then UV, then visible, then infrared radiations, then microwaves, then radio waves. So this is arranged in the increasing order of wavelength. So the one which has got the maximum wavelength is radio waves, and one which is having the minimum lowest wavelength or the least wavelength, that is the cosmic rays. So this, in the electromagnetic spectrum, the electromagnetic radiations are arranged in terms of lambda or wavelength or frequency. So in the increasing order of wavelength, the first one is cosmic ray, gamma ray, X-ray, UV, visible, infrared, microwaves and radio waves. And this is in terms of increasing order of wavelength. And if we are moving like this, it will be in the form of increasing frequency. Okay, so this is increasing wavelength and this is increasing frequency. Then the next one, that is the Born-Oppenheimer approximation. This is very important. It is usually asked in a section B part. Okay, Born-Oppenheimer approximation. Born-Oppenheimer approximation. So here in this Born-Oppenheimer approximation, we are discussing the spectra of molecules, that is the molecular spectra. Molecular spectra we already had seen, that is the molecular spectra, it arises due to the interaction of electromagnetic radiations with molecules, isn't it? So here this molecular spectra, it has got three types of transitions, that is the rotational transition, the vibrational transition and also the electronic transitions. Okay, sorry. And also the electronic transitions. And also here, according to Born-Oppenheimer approximation, the total energy of a molecule, it will be equal to the sum of all these. Okay, the total energy will be of a molecule will be equal to translational energy. The total energy of a molecule will be equal to the sum of the translational energy plus rotational energy, plus rotational energy plus vibrational energy plus electronic energy. Electronic. Okay, the total energy of a molecule, according to Oppenheimer approximation, the total energy of a molecule will be equal to the sum of the translational energy, rotational energy, vibrational energy, and electronic energy. And also in all these cases, the rotational, vibrational, and electronic energies, they are quantized. These three energies are quantized. And also in the case of translational energy, it is negligibly small. Okay, the translational energy, it is negligibly small, and so we can neglect this translational energy, and thus Born-Oppenheimer approximation, according to Born-Oppenheimer approximation, the total energy E of a molecule will be equal to the sum of the rotational energies, that is E rotational plus E vibrational plus E electronic. Okay, the total energy of a molecule will be equal to the sum of rotational, vibrational, and electronic energies of a molecule. And also we can say that E electronic, it will be maximum. Electronic energy will be maximum, it will be very high. Then comes the vibrational energy, then comes the rotational energy, and then comes the translational energy. The translational energy, it is negligibly small, and this electronic energy, it is extremely high. So according to Born-Oppenheimer approximation, we can neglect this translational energy, and the total energy will be given by the sum of rotational plus vibrational plus electronic energies. Okay, and also this is the order of energies, or the electronic energy will be maximum, then comes vibrational energy, then comes rotational energy, and then comes the translational energy. Okay, so this is Born-Oppenheimer approximation, and this is very, very important. It is usually asked in 2-mark question. Okay, so in the next session we can see the mechanism of interaction of radiation with matter. That is, we have to go through the radio frequency waves, then the microwaves, then IR radiations, then visible and UV. And as a result of all these radiations, interaction of all these radiations with the matter, different types of spectra will be arising. Okay, we have seen this molecular spectra with different energy levels. That is the rotational energy levels, vibrational energy levels, and the electronic energy levels. And these three you have to study in detail. And also you have to calculate the energy of such molecules having rotational, vibrational, and electronic transitions. Okay, so these three you have to study in detail. Rotational transitions or rotational spectra, vibrational spectra, and electronic spectra. Okay, so for today this will be okay. And also you have to write the lecture notes and submit it in our classroom. Okay, thank you.